In Module 8 of Chapter 20, we're finally going to turn to Ito's lemma, which, as I may have noted before, is probably the most powerful mathematical tool in finance today. It provides a way of identifying, if you know the stochastic process that governs the stock prices, it allows you to identify the stochastic process that governs the price process of all derivative securities on that stock. And the interesting thing is that we can then use those tools to construct a replicating portfolio, much as we did in the binomial lattice construction. And by virtue of constructing that replicating portfolio, price the option by virtue of a partial differential equation. In an earlier chapter, we saw what was called the Black-Scholes partial differential equation. We will see that that comes from the tools of Ito's lemma, which is to say, Ito's lemma tells us the process that an option price process must obey. And with that, we can construct a replicating portfolio. And by a clever trick that we, in fact, have already implemented on the binomial lattice, we will convert that information into a partial differential equation. And with this tool, the prices of derivative securities then can be determined by solving these differential equations, or at least that's one method that one can apply this mathematics. So Ito's lemma starts with a price process for stock, and we'll use the real-world price process here. Alpha and delta are as they were in the prior module. The total return alpha, the dividend return delta. So alpha minus delta is the capital gain return. We have the usual vol sigma dz. And the question that Ito's lemma addresses is, if we know that S of t satisfies a given process, and here we're going to assume geometric Brownian motion, but Ito's lemma is far more general. But we're now going to apply Ito's lemma to the assumption that S is geometric Brownian motion. What Ito's lemma determines is, or I should say, what Ito's lemma does is to answer the following question. Is there a stochastic process that the price of an option obeys? And here I wrote it notationally as some very general drift coefficient mu, which might be a function of stock prices and time, some very general volatility function sigma, which again might be a function of... Is there some function, mu and sigma, that defines the price process of an option on S? And if so, how do we determine these coefficient functions? And Ito's lemma, in fact, gives us the complete answer. It requires that the price function has some derivatives, because we're going to see that the coefficient functions in the C process require two derivatives of C with respect to S and one derivative of C with respect to T. So C has to have a little bit of smoothness to allow us taking its derivatives. But then what Ito's process says is simply, can be stated this way. Now, the mystery in this first, and I'll look at the second formula in a moment, the mystery in this first formula is the middle term. Because those of you who have studied calculus of two variables might say the first and the third term makes sense. If I want the differential of C, and C is a function of two variables, I should take the S derivative of C multiplied by ds. I should take the T derivative of C multiplied by dt. And what we have is Ito's lemma says, in addition to that, that's what you would get from ordinary calculus of a function, there is an additional term in the middle. And the additional term is related to the second derivative of C with respect to S, and we have a ds squared. ds is the process that S follows, squared. And when we multiply out ds squared and ds, we get this second equation, which is how most people think of the statement of the Ito process, of the Ito lemma. But again, I like to see it written in the first statement first because it shows you that there's really something different going on with Ito processes, that unlike calculus, where we would expect the first term and the third term, the middle term is something new, and it has something to do with the dz term. Now, the question becomes, how do we go from the first to the middle equation? And the answer is we need to use some rules that we saw earlier on how to multiply dt's and dz's, and I'll get to that in just a minute. And so the point I was just making is that this extra term is the surprise term that comes out of Ito, and it comes from the fact that the S process has a dz term in it. And what is said here is that if I started with an S process that had no dz term, this would be a differential from ordinary calculus. I would take the S derivative times ds, the t derivative times dt, and I would be done. But because of the dz term, that creates extra variability, and that extra variability gets manifested in the second derivative of S. Let's see the math of how that's done, and we're going to use the rules of manipulating differentials we saw in the prior module.